In this video, we're going to talk about density functions. And this is relevant when you have a random variable that's a continuous random variable. So random variables are either discrete or continuous. If you have a discrete variable, that's when your random variable takes on discrete values. So for instance, the number of successes, right, the number of wins in a game, it's going to be an integer. But you can have a random variable where the values aren't necessarily integers, they can be any real number. So for instance, you could have something like the weight of a person, right? Or you can have the time it takes to go from one place to another, and you might be interested in the probability of that. So the difference between, so this is when you have a continuous random variable. The difference between a discrete random variable and a continuous random variable in terms of the probability is that if you have a continuous random variable x, then the probability that x is any specific value is actually 0. Because what's happening is you think of the random variable x as taking possible real numbers, and the probability, so now instead of a probability of x equals k, you have something where you have the probability that x is between a and b. So like the probability that a is between a and b, that x is between a and b, could be represented by the area under this curve. Instead. So for instance, the time it takes to get from your house to work, or where you live to work, or to school, or wherever, to the store, right? It's not going to be, when we're talking about probability, we can't have the probability that it's exactly 2 or something. We can only talk about it for a certain range. Because if you think about it, if you had a specific value, so let's say the probability that it takes exactly 2 hours to get to the store is like 0.001 or something, well then you can do that for all the different values in your real number line, and then the sum of the probabilities would be greater than 1, right? It would be infinite because you're summing an infinite number of probabilities. So it has to be 0. So the only thing you can really do is talk about the probability that you're within an interval. So notice that when you say that the probability that x is 2 is 0, right, for a continuous random variable, it doesn't mean that's impossible. I mean, when you go to the store, right, you're going to arrive at a certain time. So, but the probability that you arrive at that time is 0. So that's something that's counterintuitive, but by the laws of probability, it has to be that way. So, one difference between the discrete distribution and the continuous distribution, continuous random variable, is that when the probability is 0, that doesn't mean that it's impossible. Like it's, right? So that's something that's takes a bit of getting used to. So instead, when we talk about finding the probability of events when you have a continuous random variable, what we have is a density function f. So here's the graph of f. It's called a density function. Density function. we say that a random variable, x, has a continuous distribution with density function f if for all a less than b, we have that the probability that x is between a and b is equal to the integral from a to b of f of x. So the area under this curve is the probability that x is between a and b. Okay. But for the purpose, so we mentioned that strictly speaking, you can't think of the f of x as the probability that x is equal to a, right? So f of a, if you plug in f of a, you get this value, right? But you don't think of that as the it's not literally the probability that x is a. However, intuitively, you can think of f of x as the probability that x is equal to little x. So the reason why you can do this is because if you look at, let's say that you take a really small distance. So you go to a plus, say, delta x. So the probability that x is between a and a plus delta x is equal to the integral of f of x from a to a plus delta x. And if delta x is small, this area under the curve is approximately the area of the rectangle, right? It's approximately, you can look at the left approximation where you look at the rectangle where the height is f of a. So it's approximately this. So it's approximately f of a times delta x. And now, what happens as delta x approaches 0? Well, you see that the probability that x is a, you get the probability that x is a on the left, and then you get 0 on the right. But the probability, so you get 0 on both sides. But if you divide both sides by delta x of this this approximation, you get that f of a is approximately the probability that x is between a and a plus delta x divided by delta x. So that justifies how we can think of f of a as approximately the probability that x is equal to a. Right? I mean, because if you think of this probability, if you think of this as like approximately the area this f of a would be the height of the rectangle. So yeah, that's the closest you can get to thinking of f of a as the probability that x is a. I mean, strictly speaking, it doesn't make any sense, but if you multiply f of a by some small change in x, then the area that you get is approximately the area under the curve. It's approximately the probability that you are between a and a plus delta x. So that's what's going on. Okay. And we also have, so we need that f of x is greater than or equal to 0 in order for the probability to be non-negative, and we also need that the integral from negative infinity to infinity of f of x is equal to 1. Now, any function that satisfies this is called a density function. So let's look at some examples. So you can have the uniform distribution on the open interval from a to b, and that has density function 1 over b minus a when x is between a and b and 0 otherwise. So let's check that this is in fact a density function. So the integral, first of all, f of x is non-negative, right? And the integral from negative infinity to infinity of f of x, well, f of x is non-zero only from a to b, and so you just get this, and then that's just 1 over b minus a times b minus a, which is 1. Okay, so we say that a random variable has the uniform distribution if the density function is given by this. Another possibility is you could have this function f of x equals rho minus 1 times x to the minus rho, where x is greater than or equal to 1 and 0 otherwise, where rho is some number that's greater than 1. So we see that this is a non-negative function, and also let's check that this is a density function. So when you integrate from negative infinity to infinity, this is the integral from 1 to infinity of rho minus 1 to the x minus rho. And then this is just going to be rho minus 1 times x to the negative rho plus 1 over negative rho plus 1 from 1 to infinity. And then this, since rho is greater than 1, this exponent's negative. And so when this approaches infinity, you're going to get 0. So you're going to get 0 minus rho minus 1 times 1 to the negative rho plus 1 over negative rho plus 1. And then that's going to equal, you see I have a negative 1 here, right? Because this is going to equal negative parentheses rho minus 1. And then you have these two negative signs, they cancel, and you get 1. Okay. Another example is the exponential distribution. So we say that x has an exponential distribution with parameter. So x has an exponential distribution with parameter lambda if it has density function f of x equals lambda times e to the minus lambda x for x greater than or equal to 0 and 0 otherwise. Well, we see that f is non-negative again, and to check that this definition makes sense, we need to check that the integral of f of x from minus infinity to infinity is equal to 1. Well, you're just integrating from 0 to infinity, lambda e to the minus lambda x, and this is, I think, easy to see that you're going to get 1 because you get negative e to the minus lambda x from 0 to infinity, and then you're going to, so lambda is positive here. So then yeah, you have a negative thing here, and so the limit's going to be 0, and then minus negative e to the minus 0, which is equal to 1. Okay. The exponential distribution we'll see later. And then another important example is the standard normal distribution. So we say that x has the standard normal distribution if its density function is f of x equals 2 pi to the negative 1/2 e to the minus x squared over 2. So this can be written as 1 over root 2 pi e to the minus x squared over 2, right? Now this actually requires some more difficult proof because this doesn't have a closed form expression for the antiderivative. So you can't just take the antiderivative. We have to use polar coordinates. So let's check that the integral from minus infinity to infinity of f of x dx is equal to 1. The trick is that if you look, the trick is to consider two of these. So you have the integral from minus infinity to infinity of f of x dx times the integral from minus infinity to infinity of f of y dy. So I'm just using two dummy variables. Okay, so this is equal to the integral from minus infinity to infinity of e to the minus x squared over 2 times the integral from minus infinity to infinity of e to the minus y squared over 2. Right, it's this times this. And then, so here to do this, we're assuming that the integral exists. But basically, by Fubini's theorem, this is equal to the integral over R2 of e to the minus x squared plus y squared over 2 dx dy. So you're doing the integral of this function over R2. And then to do this, we can use polar coordinates. Right, so this is an indefinite integral. And so I'm sweeping some things under the rug that we can do this, but it turns out that we can do this. We can use polar coordinates, so we integrate over the circle of radius r, and then take the limit as r goes to infinity. So you have maybe capital R, just capital R, e to the minus r squared over 2 r dr d theta, right? I'm using the polar coordinate formula, the change of variables formula. And when you do this, this inside integral is going to be, let's see. So the integral from 0 to capital R of r e to the minus r squared over 2 with respect to r, I can use a u substitution. U equals maybe r squared over 2, and then du is r dr, right? So this is going to be the integral from 0 to capital R squared over 2 e to the minus u du. So this is going to be negative e to the minus u from 0 to r squared over 2. And then this is going to be negative e to the negative r squared over 2 minus negative e to the 0, so plus 1. So you get this. And so then the outer integral, you just multiply by 2 pi I mean, so you're going to get 2 pi times 1 minus e to the negative r squared over 2. And so therefore, when you take the limit as r goes to infinity of this, you just get 2 pi, right? It's 2 pi times 1 minus 0. So what we found is that the integral, this double integral, is equal to 2 pi. So therefore, right, this times this is equal to 2 pi. Well, these two have the same value. So therefore, the integral is the square root of 2 pi. Oh, I shouldn't have written f of x. I should have written, because that's not the density function. Sorry. Because I have this 1 over root 2 pi. Okay, so I should have written, let's see, 1 over root 2 pi times 1 over root 2 pi, right? So I get 1 over 2 pi here. So this double integral is equal to 1 over 2 pi times 2 pi, which is equal to 1. And so each of these is equal to 1. So that shows that you do have a density function, that this is a density function. All right, so let's review what we did today. We talked about continuous random variables, and instead of specifying the probability that x is k, which you do for a discrete random variable, for a continuous random variable, you have to specify the density function, which is the function that when you integrate it from a to b, tells you the probability that x is between a and b. And we can intuitively think of f of x as the probability that capital X is x, even though that's strictly speaking not true. Because if you have the probability that x is x and then multiply it by delta x, you get approximately the probability that x is between x and x plus delta x. Maybe I should rephrase that. It's because if you have the probability that x is a for a discrete thing, right? If you think of that and multiplying it by a width of delta x, that tells you approximately the probability that x is between a and a plus delta x. And that's equal to f of x, the integral of f of x, which is approximately f of x, or f of a times delta x. And so when you have a density function, it needs to be non-negative, and the integral from minus infinity to infinity has to be 1. And any function that satisfies that is a density function. And then we did some examples. The uniform distribution, this distribution, the exponential distribution, and the standard normal distribution. We checked that the given density functions are in fact density functions. Okay, that's it for this video.